Get started. Good morning.
Good morning.
Thank you for coming to this special seminar. It's great to see the audience from multiple colleges and multiple schools today. Okay, so it's my great honor and pleasure to have Professor David Simchi-Levi at MIT. David is a professor in engineering systems and also heading this data science lab at MIT. And as many of us know that he is one of the premier thought leaders in supply chain management and business analytics. And I'm sure that we have read many of his textbooks as well in those areas. And I try to shrink the very lengthy achievement here. And so he is a former editor-in-chief in Inform's flagship journals, the management science, also operations research, as well as the naval research logistics, and numerous highly prestigious awards. That's the keyword of the Purdue nowadays, right? Really, literally highly prestigious award, such as NAE, National Academy of Engineering, engineer member, and Inform's Impact Prize for his work in identifying and mitigating risk in a global supply chain. And he is an Inform's Fellow and MSOM Distinguished Fellow, and 2020 Inform's Cookman Award, and Ford Motor Company 2015 Engineering Excellence Award, and 2014 Inform's Wagner Prize. That's actually very unique, right? For the OR practice. Okay, so he is truly outstanding in both the academia as well as the impact in practice. And talking about the impact in practice, he founded 3 companies. All of them became part of the big companies such as IBM and Accenture. So his first company that the logic tools that the provide the software solutions on supply chain optimization, which became the IBM 2009. He co-founded another company, OPS Rules, that the providing operations analytics company, which became the Accenture in 2016. And then the third company, Opelytics, a cloud analytics platform company, which became part of the Accenture Applied the Intelligence. Let's welcome Dr. David Simchi-Levi.
Thank you. Good morning. Welcome. Thanks for inviting me. You can hear me well? Perfect. I'm going to talk about reinventing operation and supply chain management, both research and practice with data science. It's appropriate to start this talk by focusing on the environment at MIT that led to this research. At MIT, I lead the MIT Data Science Lab. The MIT Data Science Lab is a partnership between MIT and about 20 companies, focusing on some of the most challenging problems that these companies have by bringing together models, data, and analysis. The partnership is cross-industry. We have partners in oil and gas, retail, consumer packaged goods manufacturing companies, insurance, airline. You will see a few examples. And we have a global footprint. We cover different research areas. Let me give you a few examples. A large area of focus for the lab is supply chain resiliency. Most companies today focus on the resiliency of their supply chain because of what happened during COVID. We, at the MIT Data Science Lab, started focusing on supply chain resiliency way before the pandemic, starting after events like the tsunami in Japan and the flood in Thailand, if you remember, of 2011, or if you remember the volcano eruption in Iceland of 2010 events that affected companies in a variety of industry, from automotive to high-tech to pharmaceutical. We partnered with the Ford Motor Company, developed in 2012, 2013, a new way to measure the resiliency of any supply chain, identify hidden risk, and develop mitigation strategies. And we implemented our technology at the Ford Motor Company. In 2014, we published multiple papers, mostly technical, but also a Harvard Business Review piece whose objective is to explain to executives what is the framework, how we integrated it with Ford IT infrastructure, and what was the impact on Ford supply chain. That year, as was mentioned earlier, we received, think about this, we are not a software company. This is a data science lab at the university. We were selected by Ford as the best technology implemented by the company that year. So a lot of recognition within Ford to what we did. Between 2014, when the papers, the technical papers, the Harvard Business Review paper was published, and the beginning of the pandemic, I was knocking on many doors, trying to convince companies to focus on supply chain resiliency. Very little interest. Most companies focus, if some of you remember, on supply chain efficiency, on cutting costs in their supply chain. Everything changed at the beginning of the pandemic, but not in the way you expect. Think January 2020. January 2020, the pandemic was in China. It was not in North America, and it was not in Europe. My wife and I just came back from a trip to China, and I started collecting data on what's happening in China during December and the beginning of January. And very quickly, I realized that I can use the technology that I developed 6 years earlier to understand the impact of what's happening in China on supply chain in North America and Europe. And I submitted and published a paper in Harvard Business Review. The paper was written at the end of January, where we said in the title, think about AI, machine learning. We said in the title and in the first paragraph that the peak of the impact of COVID-19 on global supply chain will happen in mid-March, forcing thousands of companies to shut down or significantly reduce assembly and manufacturing activities. This is written at the end of January. And this is exactly what happened. Fortune magazine, March 17, reported the European automotive industry completely shutting down. We said mid-March. This is reported in March 17. The next day, March 18, the New York Times reported that the automotive industry in the US, in Mexico, in Canada, completely shutting down. And after that, huge interest in the capabilities that we develop. For example, Accenture signed a big contract with MIT to scale up our technology and to bring it to multiple industries. They implement our technology in automotive, CPG, high-tech, and the like. 2 months later, I published a follow-up paper in Harvard Business Review where I said companies need to apply stress tests to make sure their supply chain is ready for the next disruption. And by the way, the capabilities, the technology, the concept are all here for companies to use. And we emphasized a few industries. Life science, this is April 2020, life science, food, healthcare, and now we know semiconductor manufacturing companies. All of them need to apply these types of framework to make sure they are ready for the next disruption that will surely affect their supply chain. I was excited to see that in May of 2022, 2 years later, May of 2022, the US President Economic Report. Think about this. This is the highest decision maker in the country. The US President Economic Report had a section on supply chain resiliency specifying some of the concept and methods that came out of our lab, out of our research. So that's one important research area. A second important research area in the lab is price optimization. We at the lab developed and implemented algorithm for pricing at brick and mortar retailer. For example, it's easier for me to do it here. For example, Coppel. Coppel is a large retail chain in Mexico and Latin America. Every week, our technology price 500,000 SKUs in different stores. And the price that you will see if you buy the product in Mexico City may be different than the price that you will see if you buy the same product in, for example, Guadalajara. We also developed and implemented price optimization algorithm for online platform. For example, Zalando. Zalando is the largest online fashion retailer in Europe. Every week, our technology price 1.5 million SKUs in 23 different countries. And the price that you will see if you buy the product in Spain may not be the same as the price that you will see if you buy the product in Germany. Why? Because the relationship between demand and price may be different depending on product and country and week combination. So think about the complexity. And by the way, there is a lot of focus now on large language model. This is probably one of the first implementation where OR people are using transformers, the engine under Gen AI, to identify cannibalization, to identify relationships between demand and price, and to put on top of this an optimization engine. As we developed and implemented our price optimization algorithm, we realized an important challenge. And the challenge is, how do you convince yourself and the company that the algorithm works very well? We can test it, of course, on historical data, but that's not enough. We want to test it in a field experiment. So you tell yourself, that's not very difficult. We use A/B testing. Very quickly, you realize A/B testing does not work. Why? Because think about Zalando. Suppose you take a segment of the product, say men's shirts. There are maybe hundreds or thousands of SKUs. In A/B testing, what you will do, you will split all the SKUs into two groups, two clusters. The control, where you give Zalando people to use whatever algorithms they want, and the treatment, where you give our technology to price the product. Very quickly, you realize this is not going to work because whatever you do in the control not only affects the control, also affects the treatment. And whatever you do in the treatment not only affects treatment, but also affects control because of cannibalization. So A/B testing does not work. In this paper, we show how to design, how to optimize switchback experimentation. In switchback experimentation, instead of splitting product, we split time. For example, for the first 3 weeks, we will use only the control on all the product. And then we will switch from the control to treatment for 2 weeks. And then we switch maybe again for another 4 weeks for the control. We show how to design and implement such a strategy. This paper received a lot of exposure. Recently, P&G told us that they are using our design to test many of the strategy that they are implementing in their business. As we did this and got more and more into experimental design, we realized another challenge. Think about testing drugs. Think about a drug like Paxlovid And I think my student was here talking a little bit about this research. Think about a drug like Paxlovid. Pfizer develops a drug in the first year of COVID. Once you develop the drug, you want to experiment. The idea is relatively straightforward. You use randomized control trial to make sure that the drug is effective. In randomized control trial, you take a group of patients, you split them equally into control and treatment. Control receive placebo, treatment receives a new drug, and you compare the effectiveness, the efficacy of the drug relative to placebo. And randomized control trials have been analyzed for many, many years. They are known to be very effective in estimating the accuracy, the power of the new drug. But very quickly, you realize there is a big challenge. As Pfizer is testing the new drug, Paxlovid, they realize the new drug is effective. But still, while they realize the new drug is effective, you have 50% of the population that is receiving, of the tested population, that is receiving placebo. As a result, loss of life, loss of welfare. Here is a question. Can I design an experiment that achieves two objectives? The first is the accuracy of estimating the difference between the effectiveness of the drug and placebo, and at the same time, minimize loss of life or minimize loss of welfare. This is described in the second paper that combined, if you're familiar with data science, multi-embedded with experimental design. The next area that we focus on is personalized offering. Let me explain personalized offering with an example. If you fly today from London to Paris, when you purchase your airline ticket, we are not involved. But once you purchase the airline ticket, our system kicks in and offers you ancillary products. Priority boarding, car rental, hotel, and the offers that Stefan will get may be different than the offers that I will get because the system is learning on the fly about consumer behavior. As we started implementing our technique, we implemented it in about 10 different airline carriers, as well as online insurance companies. We realized an important challenge. When you develop and implement online learning, the algorithms are very, very sensitive to the reward function. If the reward function is linear, you need one algorithm. If the reward function is quadratic, you need a second algorithm. If it's parametric, maybe a different algorithm. This is in contrast to offline learning. In offline learning, all the data is available before you decide what to do. In offline learning, we have very powerful algorithms that are independent of the reward function. This raises a beautiful question. Is it possible to reduce online learning, where the analysis is very sensitive to the reward function, to offline learning, use whatever available for offline to solve the online learning problem? In this paper that we call Bypassing the Monster, and I'll talk about it later on, we answer that question in the affirmative. We show that there is a way to reduce the online challenging problem to an offline problem, use whatever is available for offline to solve the online, and that's the bottom line, whenever the offline is optimal, the online is optimal as well. Does this make sense? So you have a black box of tools developed over the last 50 years that I can use to solve new problems. And I'll provide more insight later on. As we implemented our techniques in the airline industry, executives in the airline industry were impressed by the performance of our algorithm, but they were wondering, how come we are not using all the offline data that they have collected over many years to improve the performance of the online learning algorithm? And so in this paper, we characterize under what condition offline data can improve the online learning process, and exactly by how much. So that's the third area that we focus on. We focus a lot on supply chain issues like inventory, transportation, and procurement. For Blue Yonder, if you're familiar with Blue Yonder or JDA, it's considered either the largest or one of the largest software company in supply chain. We developed for them an algorithm for last mile delivery. And then come Home Depot. You can see the company here. Come Home Depot. Executive at Home Depot wanted to collaborate with us, but they were not sure exactly how we can help. And so they gave us transaction data from their e-commerce channel for a period of about 5 years. Analyzing the data, we realize that revenue is extremely sensitive to speed. What do I mean? If a customer goes on Home Depot website and look at the product, if the website says you will get the product in 24 hours, the purchase probability is significantly higher than if the website said you will get it in 7 days. This suggests a beautiful opportunity for data science. Why? Because if I want to respond quickly to customer order, I want to position inventory close to market demand. I position inventory Florida, in the West Coast, in the East Coast, in the Midwest. Then I can respond quickly, increase the purchase probability, therefore increase expected revenue. But this is going to increase inventory cost, which implies increased supply chain cost. And the reverse is also true. If I want to reduce supply chain cost, I want to centralize. I want to position all inventory in central distribution center, because then I can pool uncertainties for many locations. This reduces inventory and supply chain cost, which is great. But it increases time to market, which reduces purchase probability and expected revenue. And in this paper, we show how do you find the right balance depending on the sensitivity of demand for response time. We did a lot of work with IBM and Boston Scientific. And pre-2018, we also did a lot of work with Alibaba. And finally, a lot of work on supply chain digitization for a variety of companies. One example is AB InBev. For AB InBev, they came to us at the beginning of the pandemic. They had the following challenge. Their data science team developed a very effective forecasting tool that they were using to make production and distribution decisions. But as COVID hit, consumer behavior changed, forecast accuracy went down significantly. Question is, what can you do to improve forecast accuracy? Because their entire production and supply chain decision depend on that. We show how one can use statistical learning together with pandemic modeling to dramatically improve forecast accuracy and increase it back to the original level of forecast accuracy that they had pre-pandemic. And finally, in this paper here, we show how companies can use reinforcement learning to optimize inventory decision across their entire supply chain. The one thing that I want to summarize this introduction with is to tell you about a paper that just was published. And it's a paper written for executive, where we showed how we use large language models to optimize supply chain decision. Think about this idea. We are using large language models designed to generate text that has the look and feel of text generated by human. I'm using it to make production decisions. I'm using it to make replenishment decisions. This is work that we have done together with Microsoft for Microsoft supply chain, for the cloud supply chain that the company has. And this paper was published just this month at Harvard Business Review. You can see the philosophies that I'm emphasizing. We do deep analytics, no question about that. That's what my PhD students focus on. But we complement the deep analysis with papers that are accessible to business executives, because that's where the opportunity is. I can sit in my office and dream about problems, or I can collaborate with Ford, with Schneider Electric, with Microsoft to generate new research that has an impact on bottom line. What I will do in the remaining of the time is focus on price optimization, but forget about price optimization, focus more generally on personalized offering. Remember, I told you a little bit the story of offline and online. Now I want to dig a little bit deeper into that space. So from now, it will be a little bit more technical, but not very technical. My original training is OR, like many of you. But as we started getting more data, we started getting more and more into statistical learning. And as you get more and more into statistical learning, you realize there are two major areas of research under this umbrella. One is called offline learning, and the second one is called online learning. Let me introduce each one of them very quickly. In online learning, we assume no data is available at the beginning of the process. Data is generated on the fly, and then you need to make decisions. Let me illustrate with an example. A customer arrives at a platform. The platform may be an Amazon platform. The platform may be a healthcare platform. Platform may be the airline platform that I mentioned earlier. The platform observes the characteristic of the customer, what I call feature, vector, xt, and then use that information to make a decision, A. The decision may be recommend a product. The decision may be a price for priority boarding or for a specific product. A decision may be a treatment. Once we make a decision generated by the platform, we observe the reward. For example, in the case of Amazon, did the customer buy the product or not? This reward is assumed to be generated from some unknown model, F star, which depends on the context, on X, the feature vector of the customer, and the decision that I choose. This unknown model, this F star, will be referred to as the ground truth. And our objective is to design an algorithm that will maximize the accumulated reward. Reward may be revenue, reward may be efficacy of the treatment, and so forth and so on, right? Or equivalently, minimize regret, where regret is defined as the difference between accumulated reward achieved by a decision maker who knows the ground truth and the accumulated reward achieved by our algorithm that does not know the ground truth and need to learn on the fly. Does this make sense so far? That's at a high level the online learning that we'll focus on. Offline learning is a little bit different. In offline learning, the entire data, which is assumed to be IID, is available at the beginning of the process. I am not allowed to experiment. And what I have are n data records. Each record is a triplet, including the feature of the customer, for example, the decision that was taken, and the reward. And what I want to do in offline learning, remember, I cannot generate new data. I want to develop an algorithm that will generate a predictive function f hat that will closely approximate the ground truth f star. More specifically, I want to design an algorithm such that with limited amount of data, we will generate a predictive function f hat such that with high probability, f hat will have low error compared to the ground truth F star. The only thing that is not well defined in this objective is how do I measure error. Error is measured intuitively as the average square difference between the estimated value, F hat, and the true value, F star, or more specifically, it is the expected square distance between the estimated value and the true value. This is called MSE, or mean square error. You notice these two problems are completely different. Just think about the objective. One is regret. The other one is mean square error. So far, so good? As we started getting deeper and deeper into statistical learning, we started realizing that there is a need to unify these two lines of research. We wrote multiple papers on this topic. Here are just 3 examples. In the first paper that I will focus on here, we show how we can use whatever is available for offline to solve the online problem. We call this paper bypassing the monster. Later on, I'll explain who is the monster and why I can bypass the monster. The second paper is a paper I mentioned earlier. This is where we characterize how offline data can help us improve the online learning and by how much. And the third paper is a paper focusing on experimental design when we combine offline and online experimentation. Right? And there are follow-ups to each one of these papers if anybody is interested. So I'm going to focus on the first paper that was published in Math of OR in 2022. I'll talk a little bit about the motivation, explain some of the technical challenges, why this is a hard problem, and how many and what other people have obtained in this line of research. Then hopefully convince you that we have an algorithm that is extremely simple and easy to execute, and then talk about the impact of our algorithm. So let me now be a little bit technical by defining the problem I'm focusing on. Here is the problem. We are playing a total of T rounds. Think about this as the number of customers arrived. When a customer little t arrives, we observe the feature vector of the customer. And then, so X is the feature, A is a decision. You can see here that I'm restricting myself to K possible decisions. Later on, I'll talk about extension to infinite number of decisions. Once we make a decision, we observe a reward. And the only assumption I'm making is the expected reward is the ground truth. And these ground truths belong to some class of function, big F. And our objective is to minimize regret. The class of function can be anything. You can say it can be linear, it can be parametric, it can come from neural network, from regression tree. Whatever it is, we want to make sure that we are able to solve the problem. Does this make sense? So the problem is very, very generic. Now, why this problem received enormous amount of attention in the literature? Because it captured 2 key features of sequential decision making. The first one is what I call partial feedback or banded feedback. When a customer arrives, I observe the feature vector of the customer, and then I make a decision, A. I observe the reward for that decision, but I don't know what the reward will be for other decisions. That's why in online learning, people talk about exploration-exploitation trade-off, right? So that's one important challenge. The second is heterogeneity. The effectiveness of each action depends on the feature, on who is the customer. And you can see it nicely in this figure. On this coordinate, I'm showing you different decisions, say different treatment. And on the y coordinate, I'm showing you the different feature. And if you just take this decision, you can see that the reward can go up and down depending on the customer that arrives and needs treatment. And so the problem is that the context space is huge. It's not clear how I can learn across all possible contexts. When Mohit comes, I want to make sure I understand what I need to do for Mohit. When David comes, I also want to make it. Mohit and David may be completely different in terms of how they respond to the treatment. Does this make sense? So the literature, as a result, is huge. Some of you, I'm sure, know Thompson sampling. Does somebody know when was Thompson sampling introduced by Thompson? 1933. So think about this. This is huge history for these types of problem. Only, of course, in 2000 or 98, people realized, oh, these things that were developed in 1933 is extremely effective. And people started using this algorithm in many platforms. And there are lots of applications. I just want to emphasize this one, dynamic pricing, where we, together with two of my students, Chris Ferreira, who is now at Harvard, and He Wang, who is at Georgia Tech, we use this idea to optimize price for a company like Rulala, if you're familiar with the online platform. And clearly this problem is relevant to operation and decision making. Enormous number of examples from recommendation system to price optimization all the way to personalized offering.
Quick question.
Yes?
To clarify, these features are not states. This is not a state-based
No,
model.
no.
So it's unlike an MDP.
Exactly.
Could I think
Exactly.
of this as a degenerate MDP?
I'll come back to MDP at the end when I talk about generalization. But when you talk about MDP, remember here, when I make a decision, I don't change the state of the system. State of the system is driving. In MDP, when I make a decision, so I'm going to start without MDP, a special case, like you call it degenerate MDP, and then I will generalize to MDP. Okay, so right now, it's not MDP. I'm going to generalize.
And you also had an assumption of IID.
IID on the feature.
On the feature.
Only on the feature.
But how crucial is that assumption? Like, could I have
I'm going to talk about that. The very, very good question. I'm going to specifically talk, actually, as I talk about the challenges. And just to follow on your line of questions, when you think about the IID, you have a problem in online because my decision today depends on what I learned yesterday. So the IID assumption does not hold. Does this make sense? So, but I want to elaborate on this question. So remember, we are interested in the general problem for any function class big F, meaning F star belongs to big F. There are really two challenges in this problem. One is a statistical challenge. I want to make sure that I always guarantee you give me big F, I give you the optimal regret. Right? So statistically, I want to be optimal. And then there is a computational challenge. I want to make sure that I can execute the algorithm effectively. If you look at the existing literature pre our work, algorithms were either statistically efficient or computationally efficient, but not both. For example, Thompson sampling, remember our discussion, or UCB are computationally efficient, but they guarantee optimal regret only for special function classes like parametric. On the other hand, exponential weighting, elimination algorithm guarantee optimal regret, but they are completely inefficient. So what is the research question? Here is, yes.
So I guess F star is unique.
F star is unique.
Okay.
Yes, F star is unique. I don't know it. And I need to learn on the fly.
But like in a pricing problem, you could charge too high of a price, nobody buys the product.
Yeah, so you know on the
Algorithm
extreme
tells you
point.
There is no market.
Yes, you know on the extreme, but you don't know, is it continuing linearly? Is it smooth and quadratic? You need to know.
Okay.
So what are the research questions? Let me now be very precise. Given a general function class F, for offline, we know how to deal with the problem. Remember, offline, all the data is available. So given IID offline data, remember, IID offline data, we know how to find a predictor F hat that achieves the lowest estimation error and can be efficiently executed. Large classes of, independent of the reward function that I can execute. Here is what I want to do. I want to reduce the general online problem to offline and use the toolkit that was developed for offline to solve the online problem. More specifically, given a general class F and an offline regression oracle, maybe least square, maybe ridge, or maybe your favorite oracle algorithm that you want to use, can we design an algorithm for the online problem that will achieve optimal regret whenever the offline algorithm has the optimal MSE, mean square error? So when the offline is optimal, I want the online. Remember, the objectives are different. And it can be executed by just a few calls to the offline regression oracle. Does this make sense? So I want to be statistically optimal and computationally optimal. This problem, the way I now describe it, has been mentioned as an open problem in the CS literature by many, many papers. Here are a few examples. And that's where we got some credit for Microsoft research. Remember, we did recently, but the reason most of this research came from people associated with Microsoft. So why this is a challenging problem? And people have looked at this for the last 20 or 30 years. There are two key issues. The first, if you look at algorithms like UCB and Thompson sampling, they work only when you make assumptions that the reward function belong to certain parametric class. And the reason they need that is because these algorithms are able to construct confidence interval for every pair of XNA. Remember, I talked about Mohit and myself. I said his characteristics are different than me. These algorithms are able to generate confidence interval for any pair of XNA. But we know that we can do it from statistics. We can do it for simple function classes. We cannot do it for general function classes. Because of this observation, Dylan Foster, in his PhD at Cornell, and his co-authors, developed a computationally efficient algorithm that rely on confidence bound, like UBC and like Thompson sampling, by calling offline regression. So this is the idea that we have. But because they rely on building confidence intervals, they can do it only for simple function classes. So their algorithm is computationally efficient, but suboptimal in general. Does this make sense? The second problem is the IID. Remember, in the offline toolkit, the assumption is the data is IID, but my data in online is not IID because, as I observed earlier, whatever decision I make now depends on what I learned yesterday. So there is clearly dependency between the data that I receive and the decisions that I make. Because of this, now to answer your question, Dylan Foster, the same Dylan Foster from the previous slide, who was now a postdoc at MIT in the same unit that where I am at MIT's College of Computing, together with Sasha Rackling, developed an optimal algorithm that assumes access not to offline regression, but to online regression oracle. The beauty of online regression oracle is that they provide statistical guarantee for any data. I don't need to assume IID. Even data that come from an adversary, that try to fight the execution of your algorithm. So this is beautiful because it guarantees optimality. Problem is efficient algorithms for the required online regression oracle exist only in very special cases, when the function class is very simple. So we are hitting this boundary. When the function class is simple, we can do it, cannot do it in general. Right? That year, so they put their paper in January. We posted our paper 3 months later in March. And basically, we show an optimal and efficient reduction. Think about this as black box reduction from the general online problem to offline regression. We rely on an old paper by Abe and Long. This is a 1999 paper that apply, and I'll tell you what the idea is, apply one unique idea for linear contextual bandit. When the reward function is linear, we rely on their idea, and then we show that we can connect 3 different lines of research, basically with a completely different analysis than what exists in the literature. But the bottom line is, if tomorrow we can improve offline learning, immediately translate into improvement in online learning. Right? So this does not rely on the specific of your online learning model. And the MDP will come once I explain what's happening here. So let me put our result in context. One of the first, not the first, but one of the first algorithm for the general contextual bandit, Agrawal and others, guarantee optimality to find the optimal regret, but it's completely intractable because the size of the computation is the size of the function class. Then 2 years later, a group, a few people from the first paper showed that they can do better. They develop a new algorithm that guarantee to find the optimal regret by making polynomial number of call to offline classification oracle. If you know a little bit about data science, offline classification oracle requires solving NP hard problems. So it's polynomial, but each problem requires enormous amount of computation. Again, this is not achieving what we want. The third one is the paper that I mentioned by Foster, coming out of his PhD at Cornell. He developed an algorithm that makes polynomial number of calls to offline regression oracles. This is exactly what I want to do, but the algorithm is suboptimal. Right? Does not guarantee regret. And then Sasha Racklin and Dylan Foster developed this beautiful idea where they guarantee to find the optimal regret by making linear number of calls to online regression oracles, but there are just very few function classes for which we have efficient algorithm for the associated online regression oracle. Our algorithm that we call Falcon guarantee to find the optimal regret by making log T calls. Think about this, just a few calls to an offline regression oracle. If T is unknown, and if T is known, I can refine the algorithm to reduce the number of calls to log T. So a little bit more, yes.
So capital T is the horizon?
Is how many people arrive, for example, or if these are weeks, the horizon, right? So think about this, just log T of computational complexity.
And capital K
is how many decisions. Remember, I started. Later on, I'll extend it to infinite, but for now, number of decisions. Okay? Now, remember, we call the paper bypassing the monster. So I want to tell you where the monster terminology came. It's not our idea. Monster in the contextual banded literature, monster refer to papers that introduce to algorithms that require enormous amount of computation. The first to call their paper, they call their paper the monster paper, are Dudek and his co-author. Many of them are from Microsoft Research. They develop an algorithm that guarantees to find the optimal regret. But it requires enormous, what they call monster amount of computation. Then 2014 paper, remember I mentioned earlier, develop a faster algorithm, guaranteed to find the optimal regret by making call to an offline classification oracle. This regards solving NPR model. So they said, oh, we are taming the monster. We completely bypass all the challenges by focusing on any general class of function f. Okay, so that's what I'm going to focus on. Now, the algorithm and some of the results. So our algorithm is extremely simple and has three components. The first, we introduce an epoch schedule to divide the time horizon into sub-intervals of going lengths. Does this make sense? Here is the time horizon. I'm dividing into sub-interval of going lengths. At the beginning of every sub-interval, I make a single call to the offline regression oracle to get a predictor. But I don't know if this predictor is correctly representing the ground truth. So I will, in the third element, I will use a randomization algorithm. I will randomize my algorithm because I'm not 100% sure that f hat generated in step 2 is the correct one. So far, so good. This idea of a randomized algorithm initially was introduced by Abe and Long in their 1999 paper for the linear contextual banded model. We call the algorithm fast least square regression oracle for contextual banded for obvious reasons. Okay, so let me explain now the detail of the algorithm. We introduce an epoch schedule to subdivide the time interval into a few sub-intervals. If we don't know t, we don't know how many people will arrive, then we use a geometric sequence, which implies that the number of sub-intervals is proportional to log t. If we do know, we can refine the geometric sequence to reduce the number of sub-intervals to log t. Does this make sense? Extremely simple. And what it means by construction, the length of the subinterval is exponentially increasing, which means that the oracle, the offline regression oracle, is called less and less frequently as our algorithm progresses, because I make a one call at the beginning of each subinterval. Simple. At the beginning of subinterval, I call one time to the offline regression oracle, maybe least square, maybe lasso, whatever your favorite regression oracle, to obtain a predictor f hat. Does this make sense? When I obtain the predictor f hat, I am not sure that this f hat correctly represents the ground truth f star. So I am going to randomize. I am going to use exploration-exploitation trade-off in my analysis. How do I do that? This is the sampling rule that we develop. And let me explain the sampling rule in a very intuitive way. We introduce a learning rate. Notice, we will see the role of the learning rate in a second. Notice that by inspection, as we move from one subinterval to another, the value of the learning rate increases. Right? Indicating, intuitively, you will see why, indicating that I'm more and more confident in my predictor. At the beginning, I'm not that confident, the learning rate is low. As I get more data, I'm more confident, I increase the learning rate. What role it plays? In a second. Now come round T, customer T, and I'm in epoch M, in subinterval M. I already generated my predictor f hat. Does this make sense? Customer T, little t arrive. I know the feature vector of the customer xt, given my predictor f hat, and the feature vector of the customer t xt. A t hat is the greedy action. If f hat was true, this is the best action to do, right? But I really don't know if f hat is true. And so I'm going to randomize, and I will select an action A, not the greedy action, in probability inversely proportional to the gap between my prediction at the greedy action and my prediction at action A. Does this make sense? The bigger the gap, the smaller the likelihood. Think about this as exploration. I'm exploring non-greedy action. And with the remaining probability, I select the greedy action. Think about this as the exploitation. If f hat was true, this would be the best decision. Right? Notice something important. The probability of selecting the non-greedy action depends on the learning rate. What it implies is that as I move from epoch to epoch, from subinterval to subinterval, I'm more confident with my predictor f hat, and therefore the probability of selecting the non-greedy action decreases significantly. That's why I highlighted the learning rate is increasing as I move from one epoch to another. Here is what we prove. Yes?
I'm almost there. But typically I have curves where I have diminishing returns. What you are basically saying in learning, right? I learn something, I learn the next thing, I learn the next thing. At some point I know almost everything, I get diminishing returns. But you say here exactly the opposite. Why?
So I'm not sure why I'm saying the opposite. What I'm saying is, as I learn more and more, I use more frequently the greedy action.
Oh, sure, yes. Okay.
Right? Because I'm more confident that the
Yes,
predictor is correct there for the greedy action.
Oh, okay, thank you.
Does this make sense?
Yeah.
So what can we say about this algorithm? The algorithm, you can see, is very simple. Also, it's very easy to implement. So let's start with a simple case where we have a finite function class. So remember, f is just finite. We show that our algorithm guarantee an expected regret no more than a constant times square root of k t log of f, with log t calls to a least square regression oracle. If t is unknown, if t is known, we can reduce it to log t. The beauty of this result is that there is a matching lower bound suggesting that our algorithm is optimal. Now you say, okay, finite class is a simple case. What about general? Here is general. For general function class, here is the setting. Given an IID samples and an offline regression oracle that generate an estimator f hat such that the expected square distance is bounded by ER. Think about ER as the estimation error guarantee. And obviously, the estimation error guarantee depends on how much data you have and what function class you deal with. Here is what we show. Given an offline regression oracle with an estimation error ER, our algorithm guarantee an expected regret no more than a constant times square root of k, number of decisions, expected estimation error guarantee times t, with the usual statement about log t and log of t. The beauty of this is that if the estimation error guarantee is optimal for offline, there is a lower bound with exactly the same structure, suggesting that our algorithm is optimal whenever the offline algorithm guarantee to provide the minimum estimation error. So that's a beautiful insight. Whenever offline is optimal, my algorithm that work completely differently with different objective is optimal as well. Yes?
So is the t inside the square root?
Outside.
Outside?
Yeah.
So it's linear regression?
Here it's linear with t. Yeah.
So the regression?
No, it's inside, sorry. It's inside the t. Yeah. So the regret is square root of t. Yeah. So example of implementing, you can see it also in my example. If f is a linear class with dimension d, then least square is proportional to D over N. As a result, we get basically what is known in the literature as the best regret. If F is linear with sparsity S, again, we get what is known as the best regret. It applies for neural network, and it applies also for other models in general. And I just want to talk about a few extensions. The first extension is the MDP. Remember, Dylan Foster and Sasha Rackling are in the same unit where I am. We joined forces, and we extended our model to reinforcement learning, to MDP. Then Asaf Zvi from Columbia University and his PhD student, look at the last name. Same last name as my student. These are twin brothers. They extended our result to infinite action. Susan Asti from Stanford and her team extended our result to misspecified model. People from USC extended our result to non-stationary. Remember your question? Non-stationary models. People from Amazon to combinatorial action. Susan Asti and her PhD student for model selection. So there were lots of follow-up immediately. We posted our paper on March 28, 2020, lots and lots of extension. And also, people verified with real data the effectiveness of our algorithm. We did it, so there is a report. It's not in the paper, it's a follow-up to the paper where we tested the algorithm. Then Agrawell, these people in yellow, tested our algorithm, and Susan Asti and her team tested our algorithm, showing superior performance for algorithms that came out of theoretical analysis. And I'll stop here.
Questions?
So your algorithm, so the offline oracle doesn't actually have access to IID data set, right? Because for each set of the distribution is access.
Beautiful. So notice how I'm designing my algorithm. At the beginning of an epoch, I have a predictor. Here's a predictor. And I use all the time the same predictor. So now everything is IID. Because I don't learn anything during this epoch.
So it's okay if it's, let's say, not IID across different epochs.
I don't care because you give me a predictor, I'm using only that predictor. So everything during the incoming epoch is IID. Does this make sense? It's like you gave me a function. I use the same function for Mohit, for Stefan, for David, or anybody else.
But the past data is from different episode, which is not IID, right?
Yeah, but I use only one episode at a time.
Okay. Thank you.
Can you just, you have had a beautiful title,
Yeah.
Reinventing OR.
Yeah. Yes.
Can you just, I think we all get it, but can you give us your statement of what the big reinvention is? To me, it's historical and real-time data and optimized based on that. But tell us what yours is.
So the great question. So I think operation management, if you think supply chain, mostly used to be focused on optimization or technology. This is a little bit different. This brings different capabilities together from statistical learning, from data science, from OR, even from economics, to make better decisions. And my best example for you, just to highlight why this is different, remember the last paper that I mentioned that just appeared in Harvard Business Review where we use large language models to make replenishment decisions. Where did we see anything like that 10 years ago, 15 years ago, 20 years ago? This is what's so powerful and so, and this is a technical answer, meaning it's an academic answer. Let me give you the business answer. To me, the business answer is before the processes were manual. Every time I needed, if I am a replenishment guy, I'm a demand planner, if I needed to understand what comes out of the machine, if I need to change the model that the machine is using, I call data scientist, I call data engineer, I say, hey, Stefan, can you help me revise the model? Stefan said, yes. Stefan disappeared, or David disappeared, come after 2 weeks, say, here it is. You can now use it. Or here it is, I understand what the recommendation is all about. So slow decision making, lack of trust, because I don't understand necessarily the decision. And as a result, lower impact, if you ask me. What this suggests, if we can remove the data scientist and the demand planner, just interact directly with the technology, faster decision making, more following adoption of the recommendation from the system because I can understand it, and most importantly, autonomous decision making. Meaning, and now I'll give you the numbers. This is at Microsoft, 20 to 40% reduction in manual decision-making process because of this. That's what's changed. I think maybe a different way of saying, and I'll stop here, before, when planners needed to make decisions, they need this community, the data scientist, the data engineer. What this suggests is there is a role for the data scientist and data engineer, but it's more in training these models. But once the models are trained, you can automate processes.
You really move from planning
Exactly.
to execution.
Exactly.
And that's really the dramatic change.
Exactly.
Every time I get new data, which can happen every millisecond,
Yes.
whatever.
Yeah.
You make new and better decisions.
Exactly.
You don't go back to the data scientist.
Exactly. Exactly.
It's the dream in manufacturing.
Yes. Yes.
Jim, and then maybe.
Yeah, just, so in the econ learning literature, there would be similar types of problems, and then you would have a theorem. The theorem would be a stability theorem, so if you knew the answer to a simple version of your question, and then you would have this stability theorem, and there would be conditions under which the system would be stable and unstable. I didn't see any stability theorems here. So is there such a thing in your framework?
We need to define what we mean exactly by stability.
It means if you start locally near your solution, but you don't know the solution, are you, under what conditions would you be guaranteed to go?
So actually, that question we address in one of the papers that I mentioned. So let me remember. One of the papers in the airline, the question that they ask us, suppose I start with a price. I don't know what the optimal price. Start with a price that is close to the unknown price that is optimal. Turns out that when you start close, it takes longer. Let's repeat, this is not intuitive. It takes longer to reach the optimal decision. So, and I'm now giving you, I'm quantifying, and I'll explain why the intuition in a second. The rate of learning is inversely proportional to the square distance between the price that you guessed and the true price. Why is that? Right? Because it's not intuitive. You would think if I'm close, I will converge faster. And the reverse is true. The reason for that, remember, you give me a guess. So here is, God knows this is the truth. And Jim, give me a guess. Say, hey, start here. Since I don't know what God knows, I don't know that this is the optimal, I have to search everywhere. So I'm starting searching here, I'm starting here. It takes me much slower to converge relative to one that started there. And we prove in the paper, we show this square distance law theoretically, and then with a lot of experiment, with real data, we show this is indeed the case. Which is really a great question that we discover just by time, and we call it the robustness of the solution.
So next class is coming, so we take a Mohit as last question, and then we will.
My question was related to the function class. So you said that within the function class we have an offline regression oracle. I would have thought that in many of these, especially AI-oriented learning technologies, the function class itself is being learned over time, right? So is there any extension where the function class can adapt over?
Yes,
over that
so
class?
So this is, remember I talked about one extension. So one extension was by Susan Asti for F is misspecified. So you say, hey, Mohit, the function is linear, but actually it's not. They show I can use this idea that came from us, Falcon, to deal with this situation. But the core is Falcon.
Okay,
Thank
let's
you.
thank David.